Hello and welcome to this PIR Live Event webinar, brought to you in part by Partners in Research Canada. My name is Ben Hobbs, and I will be your host today. So without further ado, today's guest is Dr. Theresa Stotesbury, Senior Lecturer in the Department of Chemistry and Forensic Science at Trent University. Thank you for joining us, Dr. Stotesbury. I'll let you take it from here.
All right. Well, hi, everyone. Thank you so much for coming out to my webinar. And I hope, I'm sure some of you guys are here to learn a little bit about forensic science and what we do in the classroom and at the crime scene. So we'll talk a little bit about forensic science, and then more particularly what I'm really passionate about and my research in Canada on designing forensic blood substitutes so that we can make a bunch of different types of synthetic materials to behave like blood in a crime scene context. So sit back, relax, and enjoy. So we'll talk a little bit about forensic science as a whole. Then we'll speak to blood substitutes and how you can even make your own blood substitute and create some bloodstain patterns in the classroom. And of course, I'm totally happy to take any questions from you guys. All right, so forensic science, it's really an interdisciplinary science. When we think about forensic science and what does it actually mean? Well, really, we're talking about the study of traces, coming back to those fundamental principles of every contact making some sort of trace on a substrate, whether it's visible to our eyes or invisible to our eyes. We call that evidence, latent evidence. But really, all we're trying to do is figure out and study that matter and figure out how did that trace get there. Okay, so we really rely on lots of different concepts from the sciences, the maths, social sciences, really everything. So we can think of it as any type of science or phenomenon that can be applied to the law. So there are some major players in the field of forensic science. These really include our major stakeholders, really are the justice system, the police, any laboratory members or any type of personnel associated with that. And then there's us at universities and academia. And it's kind of like a web. We all work together. There's definitely some synergies, sometimes some tensions. That's life. But we all try to work together in order to promote the discipline to figure out best really how to characterize these traces as it's related to crime scenes. So I would consider myself as a forensic research scientist. And what does it mean? What does a forensic research scientist mean? What does it actually entail? Well, most of the time we spend our time focusing on specific research questions that are directly related to the applied context. And in our case, our space is really working in crime scene investigation. So for the most part, we take fundamental principles, and what I do in the sciences is take fundamental principles in the sciences and apply them to practical scenarios, like a crime scene investigation or any sort of case-specific experimentation, things like that. So there are in Canada and around the world, we have lots of different types of forensic research scientists, some in anthropology, myself in chemistry and bloodstain pattern analysis. Those work in fingerprints and statistics, toxicology, genetics, you name it. There's lots of research scientists that are like us. What we really do, and some forensic research scientists that aren't housed in academia, they support frontline members in forensic science, whether it's at a police agency or helping our civilian members out. Really what we're doing is supporting people who have research questions. Maybe their chemicals aren't working at a scene. How can we help that? Or maybe we're trying to find new ways to improve the evidence detection or chemical enhancement of fingerprints, things like that. We spend a lot of time also consulting and training. So I've had a lot of fun in the past few years training police in certain concepts in physics and chemistry and bloodstain pattern analysis. So you will find us sometimes in the back end, a portion of consulting and in training. What's really exciting, and we take everything out from a bird's eye perspective, a lot of us do get involved in policy and decision making, particularly in best practices in forensic science and our discipline moving forward, because we're definitely an evolving discipline. We're at kind of this paradigm where we're maturing as a field. We really are honing in on our key scientific principles, and yeah, so it's quite nice that we get involved in that way. Now, when most people ask me, Theresa, you're a blood stain pattern analyst. They immediately think of Dexter, and you guys may have seen Dexter, that media show. That's not necessarily me when I think about Dexter in the media. I'm mostly this little Dexter's Lab on the bottom right corner, that character there. So blood stain pattern analysis, let's just talk about it and a definition of it for just a second here. So when we talk about blood stain pattern analysis, really it's the study of the size and the shape and the distribution of blood stains. So we look at all these objective and measurable quantities of blood found anywhere really at a crime scene or on any sort of surfaces. And what we try to do is study them and use scientific principles to figure out how that blood or how that fluid was deposited on the surface. So we try to figure out those physical events that really gave rise to their origin. How do we do that? Well, if you're thinking about how to get into forensics or how to get into blood stain pattern analysis as a whole, particularly for those of you listening in high school, it's really important that you take a lot of math and science courses. So we do integrate lots of concepts from biology, physics, chemistry, and mathematics. And where I kind of fit in the research in Canadian research is really from a material science and engineering perspective. So what do I do as a forensic research scientist and a forensic material scientist? Really, I take and I create polymers, or I create lots of different materials. I get to invent them in the lab and make them behave like blood would at a crime scene. Okay, how do I do that, or what's the basis for the science behind that? Well, we know that blood's a material. If we think of blood and we put our hat on as a material scientist, we can think of blood as being a material, and we can really hone in on those measurable and reproducible characteristics that are useful to things like crime scene reconstruction, any sort of research and training. So I make polymers. I figure out what do I do in other words is I figure out what are the special components about blood, and how can I make fake blood do the same thing. So can I change maybe the chemical components of it? Can I add different solvents in there? Can I don't know, make it dry a certain way, react a certain way, behave biologically a certain way to behave like blood? Okay, and you might be thinking, well, why would we do that if why can't we just use blood in our crime scene labs or training or exercises? Well, there is actually a need to develop these fake blood substitutes or forensic blood substitutes, because blood can sometimes be really, really difficult to work with. And it also often, the blood substitutes kind of like in media, like they might look really gory, but they don't actually physically behave like blood would, with held to a scientific rigorous two that we would expect in the forensic sciences. Okay, so I'm going to show you a quick little 1-minute video that two of my graduate students put together that explains our research. So hopefully this makes a little clearer image of what we do in the lab. So I'll play it now.
Blood. In forensic science, this unique fluid can tell us a lot about a crime. The more we know about blood's behavior, the more we can learn from a scene. We use blood to study blood. Now what if I told you that this isn't blood?
At Trent University, members of our research group have developed a forensic synthetic blood substitute, the FBS. This fluid not only looks like blood, but is designed to act like blood, providing a novel material for forensic research and training. Previous work demonstrates that the FBS mimics the complex properties of blood. Students, researchers, and police agencies are using this material to create and study bloodstain patterns. In forensic investigations, chemicals are used to uncover bloodstains. We've designed the FBS to do the same. We are also working on adding genetic material into the FBS for use in forensic DNA analyses.
Our fluid is a safe and ethical alternative to using human or animal blood. With this material, we can train current and future forensic professionals.
I'm Amanda Orr.
I'm Sumiko Polacco, and we're making an impact in forensic science research.
So that was a nice little video that my students put together for
blood.
an NSERC
in forensic science
promotional video. So at the end of the day, the take-home messages about making blood substitutes are that we can make materials that are safe and easy to use, say in the classroom or particularly in the training environment. So they definitely bypass a lot of health and safety standards. They're free of bloodborne pathogens. Sometimes it's really difficult to work with blood because naturally our body, if our capillaries are cut or any of, we're naturally made so that our blood clots, right? We polymerize our fibrinogen into the fibrin networks, it clots. So it's very difficult to work with it. So there's a really, really tiny shelf life with blood. So we can make polymers that have longer shelf lives and actually behave like blood would at a crime scene. That makes our work a lot easier in research and academia because sometimes it takes us weeks, if not months, to do experiments. Our blood substitutes can be cost effective. Sometimes it's really costly to buy blood. You don't need, it bypasses any needs for ethical approval. And the real important and scientific part about my research is that we're really standardizing fluid properties when we do our research, because we know specific blood properties are quite variable. There's inter and intra-specific variation, so we can make our polymers have a kind of standardized properties so that we can make our experiments hopefully reproducible at the end of the day. So what makes a good blood substitute? This is a new world for us and in forensics. So we actually really had to put on our thinking caps and say, what is it? Is it just the color? Is it things like viscosity, density, surface tension? Is it like the patterns themselves? What makes a good substitute? So we recommended 4 real considerations. If you're thinking about making or designing blood substitutes or you're interested in our research, we really focus a lot of our work on these main concepts. So first of all, if you're going to make a blood substitute, we think it should be chemically safe, preferably free of biohazardous risks. Importantly, it holds scientific validity in a relevant forensic context, meaning that it behaves like blood would at a crime scene. As a material scientist, it should be pretty easy to use and fabricate. And for us in academia, we really are interested in designing new systems that can be quite advantageous in the classroom. So could they actually have added benefits for learning and education? So we do things like add nice glow in the dark fluorescent and phosphorescent fillers so we can get into nice information about complex reasoning at crime scenes. And that's the topic for another day. I think I only have a few minutes, so I'll quickly talk about 2 of the main projects that we worked on. One of the first one was really making a blood substitute that spatters and spreads the same way blood would at a scene. 3 real properties that are important with that include viscosity, so kind of the resistance to flow, surface tension, and density. So we spend a lot of time looking at what you're seeing here on the bottom of the screen is viscosity profile, blood, and our blood substitutes. It's a shear thinning material, meaning that the more force that you put onto the material, its viscosity decreases. In the classroom, you can look at different blood stains and how they actually form by looking at the influence of impact velocity or dripping height, so the influence of height on how the size and the shape of a blood stain. What you can do is look at things like, so if you create your own blood substitute or you just are interested in learning a little bit more about what we do in forensics, you can look at things like the diameter of the stain. This is so if you drop a stain about 90 degrees or perpendicular to a target surface, you can count things like the little edge characteristics like the spines and scallops, and you can plot how they actually change. So for example, this is a drip stain diameter as a function of dripping height. And so we spend a lot of time looking at and building and reconstructing models to figure out how high was the blood source. That's what we call it in forensics. How high was the blood source, or where was the blood source positioned in space during the time of the bloodletting event? Other things, I have about a minute, other things that we do, and this is really fun. This is a paper that just came out last month, or actually a few weeks ago in the literature. We have created blood substitutes that react with luminol. So if you've ever seen any crime shows and they bring their chemicals and they spray the chemical and then it chemiluminesces blue, we've created a blood-free substitute that does the same thing. So we spend a lot of time really optimizing the chemistry and really the kinetics of the chemiluminescent reaction. And have made a blood substitute for that. Here's just some examples of it glowing. This is our blood substitute at different dilutions here on the far left, the top and the bottom, the top being the higher concentration of the enzyme that we included in our polymer, down below a lower concentration, and we can see how the chemiluminescence emission intensity changes over time and changes as a function of concentration. Okay, so that's pretty much all I had. for my talk. I'm really excited to answer some of your questions. And I always say, if you're interested in science and math, do it, take it. And remember, the best education is through conversation. So if you ever need to get a hold of me, you can email me at my Trent University account. Or alternatively, if you're just interested in learning more about blood substitutes and what we're doing here at Trent University in forensic science research, you can check out our research group's website at www.impactscientific.ca.
So Theresa, to start you off today, how do you go about mimicking those properties of blood that you're trying to really get into those blood substitutes?
Okay, well, the first thing that's the most important thing is, in order to make or mimic blood, you have to really study blood. So we spend a lot of time looking at how blood's viscosity and density and surface tension and a bunch of other characteristics, like we've characterized them in a population, and also how they change over time, and how we created all these databases and collected a bunch of measurable characteristics, but how these patterns form. And then we said, okay, let's take some polymers. So our fake blood substitute is made from a silicon hybrid organic inorganic polymer. What does that mean? It just means it's actually like kind of like a flexible glassy material. So we've really spent a lot of time taking those polymers and changing their solvent, changing their concentration, changing things that we've added to them in order to look more like blood and behave more like blood.
So that polymer that you create, does that have the same texture as blood would itself too?
The polymer, so it is a liquid glass, which has some inherent different material properties, but we've designed the polymer so that it will dry and flake over time. So it does mimic some of the drying and some of the simulation type characteristics that blood would. Now, this is a lifelong experiment, so it's never going, I mean, the eternal quest is to make something exactly like blood. Very difficult to do. So we are continually optimizing our material over time. Yeah.
Well, thank you. Could you maybe describe to us what an average day for you looks like as a forensic scientist?
Right. Okay. So, and I'll say it as a forensic research scientist because I'm at a university. So I don't do a lot. I don't do casework. I'm not actively involved in casework. But my day mostly consists of I teach some courses in forensic chemistry. So if you're interested in that, Trent University has a new forensic chemistry degree program. So I'll spend some time teaching, and then I'll go down to my research lab, see what's going on with my students. I've got one student validating blood properties on bovine blood, see if it's a good simulant for crime scene stuff. I have another student who's trying to figure out how to age a blood stain. So can she use characteristics with light and how light interacts with and really with the blood stain and even the DNA to figure out a better estimate for its age, which is useful in cold cases. And I also have a graduate student who's looking at immobilizing synthetic DNA strands onto our colloid so that we can make a biologically similar blood substitute. So I'll check in with them, maybe do a little bit of research on my own, read the literature, and prep for class.
So during your presentation, you listed a bunch of those properties that you attempt to mimic in these synthetic blood substitutes. What is the most difficult one to copy?
Oh, that's a good question. I should also mention, I should caveat that our blood substitutes, they're not medicinal ones, or they're not medical, so we don't put them into our body. These are just merely to mimic blood outside of the body. So some things that are difficult or trade-offs are when we add in different components into our colloids. The surface tension of the material or the droplets that form change, which means inherently that the droplet size can change, which has a direct influence on what the patterns look like. So surface tension is a really important property to control, and we can modify that and change it by adding like surfactants, so another word for soaps and things like that. another thing that is currently what we're trying to figure out is how do we get enough DNA immobilized onto the surface of our little colloids. So that's a little quest that we're working on right now, and I think will be one of the most challenging but exciting and rewarding questions that we can answer when we get that sorted.
Ms. Pitt's class is wondering, are your substitutes currently being used by crime scene reconstruction right now, or is it still in the research phase?
Yes, so our blood substitutes, if you're interested in learning where they've actually been used around the world, you can check our website out, but we have bloodstain analysts and trainers using them all around the world, everywhere from New Zealand to we helped with a basic bloodstain course in Algeria. Our students here at Trent will use it. So Canada, US, sometimes in Europe. So it is definitely being used by forensic scientists around the world.
That certainly must be cool to know that what you do is being used by so many people. Our next question today. Sorry, can you hear me still, Theresa?
Yeah.
Oh, awesome. Our next question today comes from Ms. McCaubrey's classroom, and they're wondering, could you identify the difference between someone's blood based on appearance or observations between someone's blood, I assume, and your blood substitute?
Well, hi guys. Yes, you can, because our blood substitute is not exactly blood. So we do things like we can add any color that we want to it. So we can change it to make it look from fresh to kind of aged or oxidized blood. There are some minor differences in opacity and refractive index in our materials. So yes, it doesn't, here's a little bottle of it here. So it spreads like blood would at a crime scene or reacts chemically, but it doesn't necessarily look visually identical to it. But that's, for us, it's not the point. The point is really, how does it behave like blood?
So what surprised you the most about the process of creating a forensic blood substitute?
Oh, good question. So I am a scientist. I am a chemist and material scientist, really by trade. And so sometimes if you meet scientists, they get really, really focused on specific details. And I got really, really focused on really, really minute quantities of that. Remember that stain that you saw with the spines and the scallops? So could it really, really mimic that? And I completely forgot about the color of blood. So the first one that I made was an off magenta, and I took it to the crime scene group, and they said, Theresa, like, yeah, it makes stains. That's great, but you got to make it look visually like blood too. You need that wow factor. So that for me was surprising because it kind of goes back to the beginning of my lecture where we focus on specific things, say in science and academia, but because our stakeholders are lawyers and police officers and people of the courts, we have to make sure that we're meeting all of their requirements too. So something as silly as color ended up throwing me off quite a bit, but we're back on track with that.
So our next question today is coming again from Ms. Pitt's class, and they're wondering, do you have to create a modified version of your substitute depending on the type of blood you're trying to mimic?
Yeah, good question, Ms. Pitt's class. So we have what we call our base material. So our base compound, we take this base and it's used in all of our different types of blood substitutes. So yes, we do have a few different types, but the chemistry is almost the same. The only thing we really sometimes change, if you're just interested in blood stains that spread across surfaces, we have certain types of chemical fillers that we put in. If we're interested in chemical reactivity, we add like enzymes in there that you don't necessarily need for the physical one. So at the end of the day, it would be awesome and ideal if we could put everything together and make one superpower material. But at the moment, because we're a pretty new research program, we're just focusing on specific types of materials.
So we have another question coming from Ms. Pitt's class, and they're wondering what types of degree or degrees do you have, and where did you study?
Good question. Okay, so one thing about forensic science is that we are a pretty small and new community. So we tend to stick where we learned, some of our grades do, obviously, and we go around the world too. So I actually started and did my undergrad at Trent University in Peterborough. So I studied forensic science here. And then I flew around the world and did my master's over in New Zealand in bloodstain pattern analysis. I got really hooked on there on that. And then I came back and did my PhD here at Trent. So I've been at Trent for quite a bit, and now I'm hired as a faculty member here. And it's been really, really exciting. The neat thing about forensics is, again, we're a small field, so we tend to be in certain pockets around Ontario and Canada and around the world. So that's why, and end up having my journey here at Trent, and it's been great. I've really enjoyed it. Mm-hmm.
We've just got a few minutes left today, but before we go ahead and end things, I was hoping to have you talk a little bit about your career path, why you chose it, and maybe some advice for students who are considering something similar.
Right, good question. So I don't know where you guys are at in your careers, but just remember your career journey can take you anywhere and everywhere that your mind sets you to. So if you're interested in a career in science and mathematics, go for it. It's a really exciting time to be a scientist. So how did I start? So I actually didn't know what I wanted to take. When I was in your place in high school, and I knew I wanted to go to university, but I loved physics, I loved biology, I loved chemistry, I loved math, and I thought, man, I wonder what field can I get the best of every world. And I kind of stumbled into forensics. So I took a forensic course because it said, hey, you can take all these different sciences, and that was amazing. So that's how I got into forensics. How I got into bloodstain pattern analysis was, fortunately enough, we had one of the first bloodstain analysts in Canada as a professor and was a staff sergeant at the Ontario Provincial Police here in Peterborough. And he ended up hiring me for some time to be a research scientist in the field of bloodstain pattern analysis. So that's how I got hooked onto the field. I thought it was amazing. I got to go and shadow and go and check out crime scene investigation with some forensic officers. And I thought, this is totally the world I want to be in. So I continued, and I really like research, and I really like answering scientific questions. So rather than being a crime scene investigator, which is an amazing job, for me personally, I like being in the lab and answering scientific research related questions. So I stayed in academia, finished my master's, finished my PhD, and now have this job here. So my biggest piece of advice for you guys is, if you're interested in science, stay in science. If you're interested in forensic science, now is an amazing time to be in forensic science, because we're a new field and we're just starting to mature. So there's a lot of opportunity for growth, and there's a lot of opportunity for really making a really fruitful kind of career in forensic science. So do it. Obviously, I'll put the plug in for Trent University, but there's lots of different forensic programs around Ontario and in Canada that are amazing. So, check it out and always follow your dreams.
Well, that's all the time we have for today, but thank you, Theresa, for taking the time to give us a sneak peek at the forensics world. Next week on PIR Live Event, we will be discussing stable structures with Mr. Francesco Tangora from Algonquin College. More information about these webinars and other PIR educational programs are available at pirweb.org. Thanks for tuning in, and have a wonderful day.